Today I'm going to go ahead and continue talking about the physics of magnetically confined plasmas. And before I do start doing that, I just wanted to point out that there is going to be a homework session, tutorial session this afternoon. It's not really going to be about fusion plasmas. It's going to be looking at how to solve numerically sort of advection problems in plasmas. So basically a simplified version of Landau damping. And we'll just go through different types of approaches, some of which I don't think are widely used, at least in the astrophysical community, which you might find useful. So the homework problems should be uploaded to the website, I think, by lunchtime. And I'll also have an example program that you can run if you want. So yesterday, or Wednesday, I guess now, I talked mostly about how you take a plasma, confine it with a magnetic field, and try to come up with an equilibrium configuration which is stable. Okay? And so that was all about MHD and kind of explosive instabilities that just tear the plasma apart really rapidly. Okay? What I'm going to be focusing on today is what happens when, let's imagine you've achieved such a situation. So we have a plasma, we've come up with a magnetic field configuration, and at least in terms of MHD, it's stable, everything's great, right? What we're going to find is that there are various other types of mechanisms which can slowly make things like particles and energy leak out of the plasma, and I'm going to talk about what those mechanisms may be, what kind of constraints they place on us, and how we actually try to do this on a computer. So the first question I'll be trying to address is what exactly determines sort of the movement of particles, momentum, and energy in these magnetically confined plasmas. There are a couple of possible candidates. I'm going to show you in a minute that it's going to be microturbulence, and so much of the talk today is going to be about the physics of turbulence in basically weakly collisional plasmas with a strong magnetic field. And so the practical question from the point of view of magnetic confinement fusion is how big is this turbulent transport going to be, and can we actually reduce it in some way so that we can heat the plasma up longer and put in less energy to keep fusion reactions going. And a related question, which is more of a fundamental physics question, which has more overlap with the sorts of things you'll be seeing in space and astrophysical plasmas, is really what are the properties of this microturbulence in a nearly collisionless magnetized plasma. And so by the end of the talk, I hope to focus a bit more on this fundamental physics question. Okay. So here I'm showing you a picture of this toroidally confined plasma. And if you kind of zoom out and look at the big picture, this is what you'd see. So what I'm showing you here, we have the middle of the plasma is hot because basically we're shooting beams of energy in, for instance, to heat the plasma. Here's what gets hot. Here's where all the fusion's happening. Again, at the wall, it has to be fairly cold. And so you're going to have a gradient of temperature from the inside to the outside. Right? And the temperature roughly is constant on these toroidal surfaces, so hot, and then as you go out radially inside the torus, the temperature decreases. But it turns out that even if you have this MHD stable plasma, you have small scale instabilities which will rise, which require a kinetic description. And you can see that they have various interesting properties which I'll describe over the course of the talk today. You can see that the turbulence is kind of small scale relative to the size of the system, that it seems to be stronger in some regions than in others, and that it's highly anisotropic. So it's fairly small in this direction, whereas it's quite elongated as you move kind of helically around the torus. Okay, so we'll explain why all these things happen. So the first question that I want to ask is how good does the confinement really need to be in these fusion plasmas, right? So what's happening? Well, what we'd like to have happen is we want to put some energy into the plasma, it heats it up, and if you get it hot enough, then you can start having fusion reactions between the ions in the plasma. And so once these ions fuse, they give out some energy, right? They give out a neutron, which is very energetic, and they also give out an ionized helium atom. And it's this helium atom which is charged, which is also confined by the magnetic field, and as a result, it stays in the plasma long enough to collide via the Coulomb interaction with other charged particles and give the energy to the electrons and the thermal ions. Okay? So what we'd like to have happen is we'd like to kick off this fusion process and then take these energetic helium ions and use them to keep heating the plasma and have a self-sustaining system. And at that point, you can just turn off all the energy injection and let it do its thing, okay? So for that to happen, what we need to do is we need to have the rate at which fusion reactions are occurring needs to balance the rate at which the energy is leaving the plasma. If the energy leaves the plasma too fast, then there's not enough time for these fusion reactions to heat the plasma before they leave. So roughly speaking, the balance that we're trying to strike here is one in which we have sort of the power going into the plasma due to these fusion reactions, which I write an expression for here, and I'll discuss in just a second. And that has to balance the rate at which energy is leaving the plasma. Okay? And so roughly speaking, that's going to go like the pressure of the plasma or the stored energy in the plasma over the confinement time of that energy. So this fusion power goes like basically the density squared, where the density here is the density of the ions that are doing the fusing. This is the fusion cross-section, which is a function of the temperature and has a peak in the tens of keV range. And this is the energy of those ionized helium atoms that I was talking about. And so the numbers of interest here for fusion are shown. So the densities we're looking at are 10 to the 20 particles per meter cubed. The temperatures are on the order of 10 keV. This fusion cross-section turns out to be this small number here. And the energy of these ionized helium atoms is something like 3.5 MeV. Okay? So when you take all these numbers, we plug them in, put them into this expression, what we find is that this energy confinement time that we need is on the order of a second. Okay? So we set up our macroscopically stable plasma, and we need to make sure that any slow sort of transport processes, say diffusive transport, has to be slow enough that it keeps plasma in for about a second. And so how are we going to do that? Well, without any magnetic field, without any gravity, we can just estimate how far off we are, right? So if you just imagine these particles are moving around with some thermal speed, which for the temperatures I showed you earlier, turns out to be about 10 to the 5 meters per second. And if we imagine that the largest kind of devices we're going to want to build, partially for practical purposes, such as just the fact that cost increases the bigger you make something, you're going to end up having something which is on the size of, say, meters, all right? So the amount of time it takes a particle in here, a hot particle in the middle, to leave to the edge is going to be something like 10 to the minus 5 seconds, right? So the magnetic field is going to have to do 5 orders of magnitude of work for us to get us to where we want to be. And so when we put the magnetic field in, as we know, particles just gyrate around that magnetic field line. But whenever you put in multiple particles, you're going to have Coulomb interactions between them, right? And that's what I'm trying to represent here. Let's imagine that we have a magnetic field line coming out of the board. We have a particle which is undergoing its Larmor motion, and occasionally it feels some kick which reverses the direction of its velocity. And when that direction of the velocity changes, it moves to circle about a new field line. Now, this is actually much simpler than what really happens. You don't have these kind of billiard ball-like collisions. Instead, you have many, many small angle collisions because the Coulomb interaction is a long-range interaction. But the same picture kind of works out, where the time between collisions ends up being sort of the time it takes for all these small angle collisions to have an effective 180-degree change in the velocity. So we still have movement across magnetic field lines just due to collisions. And of course, I could have also ended up colliding at this location instead of this one, and it would move me inwards instead of outwards, say. And so this is a random walk process, right? And so the probability, for instance, at some particular spatial location and time of finding the particle there is going to be half the probability that the particle was here at an earlier time, plus half the probability that the particle was here at another time, assuming this is a 1D problem, right? So if the particle's here, it has a 50-50 chance of going that way or this way, and similarly over here, right? So that's the expression I'm writing down here, where L is the distance between the centers of these gyration radii, and tau is sort of one discrete time step between collisions. So we can Taylor expand this expression about this central location x and t, use the definition of the derivative, and you end up with what you guys would all expect, which is the diffusion equation. So basically, the pressure or the probability of finding a particle at a given location is going to be dependent on some Laplacian of the pressure. And the diffusion coefficient is going to look like the step size squared over the step time. All right. So we can now estimate roughly how long, using this random walk type argument, it's going to take particles to leave the plasma due to collisions. Right? And so what we're going to do is we're going to take the estimate that I just gave you. We're going to plug in that the step size now is 1 gyro radius, and that the average time between steps is going to be some collisional time. Okay? And the collisional time is going to be the mean free path for collisions, so how long on average a particle goes in space before its velocity vector is deflected by a significant amount, divided by the thermal speed of the particles. So we have our diffusion equation to describe this process, and this gives us that the pressure over the energy confinement time is this quantity, where all I've done is I've plugged in the step time and the step size. And so this tells us that the energy confinement time looks like this. So A here is, say, a system size scale in the problem, so say a meter, right, the size of the device. And we see that that, of course, should be much, much larger than the Larmor radius if we want to have a confined plasma. And we also have this expression, lambda mean free path over the size of the system. And so in fusion plasmas, because the temperature is so high, the collisionality is really low, okay? And so the mean free path can be up to thousands of times larger than the size of the system. So both of these numbers are really large. So this one's something like 10 to the 5. This we saw earlier was 10 to the minus 5 seconds. And so the confinement time is something very large times a second, right? So if all we had were these classical collisions, then everything would be great. We would have had fusion decades and decades ago now. But we don't, and so there must be something else going on. Okay? So last time, I described something called Tam's theorem, where we said that, for instance, if you have a degree of symmetry or an axis of symmetry in the system, then you'll have a conserved quantity, and the existence of this conserved quantity ended up leading us to believe that particles will stay pretty much on a given flux surface, which is mapped out by a single magnetic field line, except there's some correction. And of course, that correction is small, so I just threw it away and said particles stay on the flux surface. Now we're wanting to consider what happens when you take into account this correction. Okay? So in particular, if this thing were exactly constant, particles would just stay on a flux surface. But it turns out that there's a correction. That correction goes like the Larmor radius over the system size times the ratio of the total magnetic field over the poloidal component of the magnetic field. Remember, the poloidal component is the component in the short way around the torus. And so in fusion plasmas, most of the field is toroidal, and so this quantity is quite large. It's something like 10. So in the end, what matters, the drifts off the surface go like this Larmor radius times this big factor 10, so it's something like this quantity rho poloidal, it's called, which is several times the Larmor radius. And so the picture I showed you last time was basically what was happening is you'd have a particle, it would try to move along the magnetic field line the short way around. The magnetic field strength changes along that magnetic field line, and so if it changes enough, the particle bounces and undergoes this sort of so-called banana orbit in the plasma. So just like with the Larmor motion, this can be interrupted by collisions. And so a particle could start moving around in this trapped orbit, and instead it could collide and move outwards or inwards. So again, we have a random walk process. And now the step size in this random walk, instead of being the gyration radius, is a gyration radius scaled up by a factor of 10 or so, okay? And so the transport will be a little bit worse. And so we can go through the same analysis that I just showed you earlier for the classical collisions, where now the step size is replaced by this poloidal Larmor radius. And what you find is that the confinement time now is the same as it was before, but it's now smaller by a factor of 100. Right? So this is, I mean, it's bad overall, but it's good because it's telling us that we're getting closer to understanding what's happening in the experiments. But still, as I said, this number can be several thousand. And so this is still a number which is much, much bigger than 1. So in most devices, if this is the only type of transport mechanism we had, again, fusion would have been solved long ago. So this is so-called neoclassical transport. And so the reason we don't have fusion right now is because it turns out there are other instabilities in the plasma that MHD doesn't capture. Okay? These are so-called toroidal drift wave instabilities. What I'm going to show, so there are a whole host of different types of drift wave instabilities that are categorized by different features. What I'm going to be showing you is something which is called the ion temperature gradient or electron temperature gradient instability. And it's ITG or ETG. It's one of the many acronyms in fusion, which confuses everyone. But basically, these are the key instabilities which people kind of look at when trying to understand turbulence in fusion plasmas. So here's the picture of how this works, right? Here's the torus, so it goes around this way. And as we saw on Wednesday and in Matt's talk on Tuesday, in this case, if you have a variation in the magnetic field strength, as we do here, because recall the magnetic field is generated by some current flowing vertically here, so the magnetic field drops off as you go out radially. So if you have a magnetic field coming out and a gradient in that magnetic field, you're going to have drifts. And the drifts are given by this expression. So if I now put a gradient in the temperature across this plasma, right? So it's going to be hot over here in the middle and cold at the edge. Then particles that are sitting in this hot region are going to move faster than those in the cold region because these drifts depend on the speed of the particles, and the typical speed of the particles is the thermal speed. All right? So particles are drifting down faster on this side than on that side. And if I perturb the surface between the hot and the cold plasma, then what you see is that you have some particles here which are drifting down fairly slowly, and some particles which are drifting down here more rapidly. All right? And so I'm focusing on ions right now. Electrons actually do the opposite thing, so they're going to reinforce what I'm about to talk about. So at this surface, you have very few particles coming in and a lot of particles coming out, or particles are moving quickly away and only slowly replenishing them. Okay? So you're going to end up with an excess of negative charge at this surface, whereas over here, positive charges are coming here rapidly, but leaving only slowly, and so you have an excess of positive charge at this surface. Okay? And the same thing alternates at the different interfaces. And so you have pluses, minuses. These give rise to electric fields, which alternate in sign in each of these regions. And this now gives us an E cross B drift in the plasma. So electric field in this region, for instance, crossed with the magnetic field, gives you a drift which accentuates the initial perturbation, and so we end up with instability. Okay? So this is the basic picture of a toroidal drift wave instability. Now, as I mentioned to you on Wednesday, it turns out the curvature of these of the plasma has a big impact on stability, and it also has a big impact in this case. So I looked at the outside, I showed it was unstable. What happens now if we look at the inside? Well, the picture looks almost identical, except for now the hot's over here and the cold's over here. And so I perturb the interface. Again, I get drift motion downwards, but now, again, particles are moving fast here, and so you have buildup of positive charge, negative charge, positive charge. And so now in this case, we have electric fields. Electric field crossed with the magnetic field gives you a drift, which is in that direction here, and that tends to stabilize the original perturbation, right? So on the inside of the plasma, this sort of perturbation is stable. So we have unstable modes on the outside of the bad curvature region, stable modes on the inside or good curvature region. And so what net effect does this have on, say, temperature gradients that we can sustain in the plasma? Because remember, we want large temperature gradients to get to a large temperature in the core. Well, we know that the growth rate of the instability in that bad curvature region must depend on the temperature gradient, right? Without the temperature gradient, this didn't exist. And yet at the same time, we know that there's some stabilizing influence on the inside of the plasma, or the good curvature region. And so how do we figure out if kind of the net stability is going to be positive or negative? Well, what you can do is you can imagine a perturbation which starts to grow in the bad curvature region of the plasma. And as it does so, of course, particles are streaming along the magnetic field. You have waves which are propagating along the magnetic field. And this takes this perturbation, which starts out in the unstable region, and moves it into the stable region. Right? And so it's going to be a competition between how fast that perturbation can grow in the bad curvature region compared to how rapidly it can move along the field line and get to the good curvature region. Okay, so in other words, the growth rate, which depends on temperature gradient, has to be bigger than some parallel time scale in the problem. And the parallel time scale we have, well, there are two of them, which are basically the same, of the same form. So one of them is just saying we take the speed of the particle that's moving along the field over the distance along the field line from the outside to the inside of the torus. And the distance along the field line, remember this field line can go around, say, many times toroidally as it goes from the outside to the inside. And that how many times it goes around toroidally is characterized by this parameter Q, the safety factor, which is the pitch of the magnetic field. So this is the rate at which particles stream from the outside to the inside of the device. Similarly, if I'd instead thought about how fast, say, an ion acoustic wave moves from the outside to the inside of the device, it would be the exact same time scale. So what this tells us is that the temperature gradient, which drives this instability, has to be bigger than some value in order to sustain that instability in a global sense. Okay? And so what this means is we have some critical temperature gradient in the plasma. All right? And so much of our understanding of how large a temperature we can sustain in our plasmas comes from this simple idea. Right? There's some critical temperature gradient, and as I'm going to argue in a moment, you can't go very high above that critical temperature gradient except in very special cases. So we know we have an instability. What spatial scale do we expect that instability to live on? So on Wednesday, all the instabilities I was talking about were MHD. They were system scale instabilities. If this one were system scale instabilities, we'd be out of luck, right? Because if you have an instability which is mixing across the entire plasma, then you're not going to maintain a very large temperature gradient, and you're not going to get fusion to work. So we hope it's small. Well, there's one thing which is fundamentally different about this type of instability compared to the ones we were talking about on Wednesday, and that's that the fundamental mechanism for it depends on these magnetic drifts. Okay? And these magnetic drifts are small. They're slow compared to the thermal motion of the plasma. Particularly, they're small by a ratio of the Larmor radius to the system size. And so already this is giving us a hint that the Larmor radius is going to be an important scale for this instability. So we can estimate roughly the growth rate of our instability by thinking about the rate at which charge separation is occurring in the system, because it was the charge separation which gave rise to the electric field, which gave rise to the E cross B drift, which is what caused the instability. So what is the rate at which this charge separation is occurring? Well, it's the time it takes particles that are moving at the drift speed to traverse one wavelength of the perturbation, or one half wavelength of the perturbation. Right? And so if I write that in terms of a rate, gamma, then it's going to go like k perp, where this is the wave number associated with this perturbation, times the drift speed. And so I can plug in our expression for the size of the drift speed, and we see this growth rate goes like V thermal over R times K perp rho. Right? So in other words, as K perp rho goes to 0, this instability is shut off. And it would seem from this expression that we would estimate that the smaller the scale of the instability, the larger the growth rate. Right? So this should go to really, really, really small scales in the plasma. This isn't quite right, because it turns out that if you start to go to very large values of K perp, then something else happens. So in particular, imagine what happens if we take a gyro radius, which is like this huge thing compared to the size of our perturbation. Right? So this is what would happen if I take the perturbation to be really, really small wavelength. Well, what's going to happen is, let's imagine you get these alternating electric fields set up, which would have driven instability. Well, your particle doesn't see just one of these electric fields. It averages over many different flips in the sign of this electric field. And by doing so, you're averaging over an oscillatory function, and you're reducing the size of the effect. Okay, so you're basically averaging out these very special conditions which give rise to the instability. And so that's what I'm showing here. And so in the end, if you go to k perp rho very, very large, then the growth rate's also going to go to 0. Okay, so k perp rho of 0, you have no growth. K perp rho large, you have no growth. And so the only choice you have is to have instabilities whose wavelengths are tied to the gyration radius of the particles. Okay. So what does that imply for some of the properties of the turbulence? So here I'm giving you just a mixing length argument for how big the fluctuations in such a plasma will be. So imagine that you have some quantity like the density. So this now is going to be the middle of the plasma volume. So if I had my torus picture here, this is going to be the middle of the plasma volume, and I'm going to be going out to the edge. This will be the edge. And so the density we want to vary, it's going to be large in the middle. We want to very slowly and decrease as we move across the plasma volume. And what I'm about to do now is I'm going to put an eddy in the middle of that plasma, which has a size comparable to the Larmor radius associated with the particle motion. So as you can see, what this is going to do is it's going to mix plasma from here and here. And so it's going to kind of flatten the density across this little region, right? So in other words, it's going to make a change in the density of size comparable to delta n here, right? And if you look at the ratio of delta n to n, then you're going to see that that just goes like the eddy size over the size of variation of this equilibrium density, right? So in other words, as long as the gyro radius is small compared to the system size, the fluctuations that we expect to see are also going to be small. Okay, so the picture you should have in mind is one in which we have fluctuations on the scale of the Larmor radius, and and it's just bubbling on top of some equilibrium situation. Okay. So let's now see how long the plasma is going to be confined in the presence of this turbulence, which comes about due to these instabilities. So just like in the classical collisional case, the random walk step size is now going to be like the Larmor radius of the particle. The average step time is going to be roughly how long it takes for an eddy to turn over and break up. Okay, because basically what you're going to expect to have happen is you have some eddy, it moves the particle across the eddy size as it starts to turn over. And once the particle this eddy breaks up, a new eddy appears and it'll move the particle in a different direction, right? So the average step size is going to be the size of the eddy. The time it takes is going to be the time for that eddy to turn over, which is given by this. It's the length of the eddy, which is rho, over the E cross B motion inside that eddy. And this gives you something which goes like A over V thermal. So again, we plug this into our diffusion equation to get an estimate for what the confinement time looks like. And it looks like this. So the energy confinement time goes like A over rho squared times A over V thermal. And these things pretty much cancel out exactly to give you about a second, right? So we're just on the borderline with this turbulent transport of getting the confinement time that we need to make fusion work, right? And so a lot of the effort that we put into things is trying to make sure it's on the right side of this 1 second and not below 1 second. Right. So here's a picture of what it actually looks like on a computer. This is taken from a gyrokinetic code called Gyro. And let me back that up. Yeah, so let me pause this before I get started. So it happens fast. Sorry about that. Yeah, so what we're about to see, what you've started seeing already, is going to be showing fluctuations in the electrostatic potential, which you can think of as density fluctuations in the plasma. I should also note that in this movie, you're not seeing the equilibrium. So this is only the fluctuations that you're looking at, right? If you saw the equilibrium, then you wouldn't see any of this stuff, because this is just low amplitude on top of the equilibrium density, for instance. Okay, and so I really wanted to see the beginning of that. So I'm going to inflict it on you again. So the first thing you're going to see here is a linear stage of the instability. This linear instability that you'll see to start out with is exactly the one that we just discussed. Can you guys actually see anything? I can see it on my computer. Anyway, what you should have seen, if you could see anything, was that there's sort of little fingers that come out to start out with. Those fingers were the linear structure of the instability. And then, of course, as that instability grows in amplitude, then you start to have nonlinear effects become important, and you get turbulence. And what you can see is that these turbulent fluctuations have scales in this direction. The scale of these fluctuations is roughly the Larmor radius, or a few Larmor radii. You can see that it tends to have sort of larger amplitude and might be a bit more elongated on the outside than on the inside. Again, because you have the instability drive on the outside and not on the inside. These perturbations are elongated along these helical structures, and the reason for that is that these helical structures map out the magnetic field lines, right? So particles are confined in the direction perpendicular to the magnetic field, but along the magnetic field they're free to stream more or less without inhibition, okay? The other thing you can notice is that you saw a lot of flows moving around in this plasma, and those flows are sort of a combination of two different things. First of all, there's something called zonal flow, which is similar to the zonal flow, for instance, that you see in Jupiter. It's just flows propagating in different directions, which automatically form self-consistently due to the turbulent interactions. And there can also be equilibrium flow shear in the plasma that we induce, because it turns out this equilibrium flow shear can actually tear apart eddies and suppress the turbulence. And I'll talk briefly about that later on. Is everything more or less understandable so far? Good. Okay. So I said earlier on that this was something that we use gyrokinetic codes to treat. But everything I've talked to you about so far has been fluid, fundamentally, right? The picture I showed you before it knew that there were drifts, but otherwise it was pretty much a fluid picture. And so we know that the collisional mean free path in these plasmas is actually long. And so the question is, what about the kinetic effects? How are they going to modify the picture that we just looked at? Well, fundamentally, the same instability is going to occur. They're just going to be a bit worse, all right? And so a couple of reasons why that might be the case is that in order to actually stabilize the instability, we said there's some competition between growth happening on the outside of the device, or the bad curvature side, and stabilization on the good curvature side. And the estimates that we came up with had to do with all particles moving at some thermal speed or some wave traveling along the field line. But in a kinetic distribution of particles, you have quite a few particles which are actually traveling slower than the thermal speed. So those will have more time to grow before they go to the good curvature side of the plasma. And furthermore, we also shown that some particles actually get trapped in the magnetic well, right? So some particles never leave the outside of the plasma. They just stay in that bad curvature region indefinitely, unless they collide, for instance. And so clearly both of these things are going to have a destabilizing effect on the plasma. And so generally speaking, what you expect to find is that the critical gradient at which the plasma might sit from a kinetic analysis will be smaller than whatever you find from a fluid analysis. So here I'm going to argue why we expect things to mostly sit at this critical gradient in the plasma. So plugging in, earlier we came up with some estimate for what this diffusion coefficient was from the turbulence, where the step size was the Larmor radius and the steps time was the turnover time of the eddy. And it looked like this, right? So the pressure has a factor of temperature inside it. The thermal speed has a factor of the square root of temperature inside it. And the square of the Larmor radius has a factor of temperature inside it. So this diffusion coefficient goes like a very strong power of the temperature in the plasma, right? So the hotter you make your plasma, the larger this diffusion coefficient becomes, right? And that means the diffusion itself becomes faster. So what this means is that in the core of the plasma, we expect that as you put more and more energy into the plasma, it just goes out very rapidly. So in other words, what I'm looking at here is, you can think of this as, in steady state, the amount of energy I put in is going to be the same amount of energy coming out. Otherwise, the profiles would be changing in time. And so energy input is the same as the rate at which energy is leaving the plasma. So here we're showing the temperature gradient, T prime, normalized by the temperature of the plasma. So this is whenever the temperature gradient scale length. And what we see is, for some low values of the temperature gradient, there was no instability, right? So I can put in a very low level of energy into the plasma, and because there's no transport coming from these micro instabilities, then the temperature gradient just grows and grows, right? Until at some point, you get this critical gradient, and then all of a sudden, because you have this very large diffusion coefficient, the heat flux in the plasma jumps up rapidly, okay? So it's a very stiff function of temperature gradient. So it doesn't matter, once you get to this point, you can increase the amount of energy you put in as much as you'd like, and you only change the temperature gradient by some tiny amount. So you're pinned to this critical gradient. However, if you go closer to the edge of the plasma, because the temperature has to eventually decrease to very low levels, then this diffusion coefficient can become small again, and so the behavior of the energy transport as a function of temperature gradient relaxes a little bit. And so what you expect to find is that in the edge of the plasma, you can sustain fairly steep temperature gradients, whereas in the core of the plasma, you're kind of pinned to whatever this critical gradient is. Okay? And that's what we see in fusion plasmas. We often see steep temperature gradients near the edge, in something called the pedestal, and basically fixed temperature gradients which are much lower over the rest of the plasma. Which means that the edge temperature is actually really important. Okay? Because we have a fixed temperature gradient across the rest of the plasma, if I can double the temperature at the edge of my plasma, that means I can double the temperature in the core of my plasma. All right? So that's the basic picture of how turbulence defines the profiles in our system. And now I want to start talking a bit about how you would actually treat this problem numerically. So how would we solve this problem on a computer? And here I'm trying to illustrate that it's pretty tough. So there are a lot of different time scales in our problem. Out here you have somewhere like the plasma frequency. I'm not even going to consider that here. We also have gyro motion for the electrons and the ions, which are happening on very fast time scales. At somewhat slower time scales, you have turbulence and collisions. And on even slower time scales, you have this evolution of the equilibrium, or the mean profiles in the plasma. And remember, this scale separation here was a result of the fact that these eddies are very, very small compared to the size of the machine. We also have quite a large range of spatial scales in the problem because we have the electron Larmor radius and the ion Larmor radius separated by the square root of the mass ratio. You have turbulence, which exists in sort of this range of spatial scales. And then you have the mean profiles again, which are separated from these Larmor motion scales by a significant amount. And then collisions are happening on even longer spatial scales. Okay? So we have to, if we're doing the direct problem, we need to include all these time scales, all these spatial scales. And as I mentioned, it's a kinetic problem. The collisions are weak. And so what effect does this have? Well, it means that we're going to have to deal with velocity space in addition to physical space and time. And so a simple picture of why we have to worry about velocity space structure is given here. So imagine this is the distribution of particles in some 1D cut. So here, say, is some coordinate z. Here's the velocity associated with that coordinate z. And if you start out with some kind of structure in space, and initially you have no structure in the velocities, right? So this is a situation in which you wouldn't really need much of a kinetic treatment because all particles are moving with the same speed, right? So you could choose any velocity you want and just deal with things in real space. And so there's a slice in velocities taken at this particular spatial location. But over time, just ballistic motion, the streaming of particles, is going to lead to structure in the velocity space, right? Because particles up here, which are moving with a positive velocity to the right, move this way. particles down here with a negative velocity to the left move that way, and particles in the middle don't move at all. Right? So if I now take a cut at the same spatial location at some later time, then we see that we now have some structure which is developed in the velocity space. And the longer you wait, or the higher the wavelength that you start out with in the physical space, then the more rapidly you're going to end up getting structure in the velocity space. And so this is what you have to resolve with a kinetic code. And that was only looking at one type of phase mixing, it's called. That was phase mixing as particles stream in the direction of the magnetic field. But there's other phase mixing mechanisms which are more complicated and a bit more interesting. And that's where you can have, for instance, nonlinear phase mixing in the system. So imagine, for instance, that these contours that we're looking at here are contours of the electrostatic potential of the turbulence, right? And so the electric field you get by going across constant electrostatic potential contours. So the local electric field here, for instance, points in that direction. And if I cross that with a magnetic field, which is out of the plane of the board here, then you find that the motion of the particles, E cross B motion, is just along these contours. Okay. Now that would be the case if these red things here, which are particles, had zero gyro radius. Right? So this is showing particles gyrating around in this electrostatic turbulence. So what particles actually see is not just the electric field at this particular point, but they see an electric field averaged over all this turbulence. Right? And so in particular, if you take two different particles, which are moving at two different perpendicular speeds, right? That's going to give them two different Larmor radii. And if their perpendicular speeds, and therefore their Larmor radii, are separated by an amount which is comparable to the size of these eddies, then the two different orbits are going to see completely different turbulence, right? If the Larmor radii were very close to each other, then they would see pretty much the same thing. But if they're sufficiently separated compared to the scale of the turbulence, then they see completely different turbulence, right? And so two particles, which are at the same spatial location but with different velocities, are going to move in essentially completely decorrelated directions, so just randomly relative to each other, right? And so what this means is that if you have a separation in your velocities comparable to the scale size of your turbulence, then you're going to end up getting small-scale structures developing in the velocity space on comparable scales. Okay? So not only are you going to find that you have structure in the distribution of particle velocities in the direction parallel to the field, but also in this v-perp coordinate. Right? So this is something that I'll try to touch on later if there's time, but everybody here is probably familiar with, well, I'm not sure everybody is, but many of you may be familiar with sort of the neutral fluid picture of turbulence, like Kolmogorov-like turbulence, where you inject energy at some large scale by stirring up the system. You could be stirring up eddies in a coffee cup, or you could have a supernova explosion which stirs up turbulence on large scales, and that turbulence eventually breaks up and goes to smaller and smaller scales, right? And the idea is that eventually you get to a small enough scale where viscosity matters. Well, via this kind of mechanism, the phase mixing in the velocity space, you also start out with large scales in velocities, so some smooth distribution, say, with a width of the thermal speed. But over time, these two mechanisms will take those smooth velocity space structures and break them up to smaller and smaller scales. And you have sort of a turbulent cascade of energy, not just in physical space, but also in velocity space. So it's a phase space cascade instead of simply a real space cascade. Okay, so that's kind of far field. What we're going to be doing then is having a kinetic description of our dynamics. And here I'm just writing down the fundamental kinetic equation. It's Vlasov equation with a collision operator. And we're going to be following the trajectories of these particles streaming along the field, oscillating about it, and drifting across. So how expensive is that to do? Well, we only need to simulate the system size, right? So we don't, even though collisions have some very long spatial scales, we don't really need to resolve those very long spatial scales, because all we're worried about is what's happening inside the plasma volume. So we can throw away everything happening out here, but then otherwise we'd be keeping everything else in the system, right? And so if I just estimate how many grid points it would take to resolve all these time scales, all these spatial scales, and even take a very coarse grid in the velocity space, say, then here's what I end up with, right? So spatial grid ends up being something like 10 to the 6 grid points in 3 dimensions. So that's 10 to the 18 grid points for resolving space. Velocity, even if I only take 10 grid points in each of the 3 spatial directions, this gives me 10 to the 3 grid points, so a total here of 10 to the 34 grid points when I take into account the fact that I have to do this for 10 to the 13 time steps. So that's just enormous, right? There's no way, there's no hope of doing this anytime in the near future on the largest computers we have available. So we have to work to do better. And so one way of doing this is by going to gyrokinetics. So this was something that Matt described earlier. I'll briefly describe it in a minute. But the basic idea is that we're going to take these sort of helical motions and average over the fast gyration that smears out the charge about these charged rings. And so instead of following this rapid oscillation, we're just going to follow charged rings as they kind of move along the field line and slowly drift across it. So this has some obvious advantages. We average out that fast time scale in the problem. And also we eliminate one of the dimensions of the phase space because we're not going to keep track of this gyro angle variable anymore. So we've reduced the dimensionality and we've eliminated some time scales. That actually helps a lot, right? So we don't have to worry about these gyro frequency time scales anymore. And here in the velocity grid, we only have 2D. So all things told, this has saved us, oh, one other thing I forgot to mention here. So as we saw from the movie, as I've been mentioning multiple times today and on Wednesday, the turbulence we're looking at and all the dynamics in these devices, because it's a very strong magnetic field, they're all, the motion is very anisotropic with respect to that magnetic field. So the other thing we're going to take advantage of with gyrokinetics is that basically k parallel is much, much smaller than k perp. And so when I take that into account, in addition to eliminating the gyro frequency and the gyro angle, then I find that I save a factor of about 10 to the 10 in the number of grid points required for my simulation. So now I'm down to the 10 to the 24 grid points, which is still very large, but it's much better than we were looking at a minute ago. But we can do even a bit better than this. So I'm going to be looking at what's called multiscale gyrokinetics, which is basically the gyrokinetics that Matt was talking about. And so the idea is it will take our distribution function f, which contains all the dynamics in the plasma, and I'm going to separate it out into 2 pieces. For you to do this, I haven't defined yet what these pieces are, but it's going to turn out that f I'll define to be the mean or the equilibrium part of the distribution function. So this will describe the slow variation in space and in time, and delta f will define sort of the fluctuating components. And if you want to think of kind of a technical definition, how would you actually split these out? You could, for instance, ensemble average your distribution function f, and what's left you could call the mean piece if you'd like. And so we're going to take advantage of this difference in scales of the equilibrium and the fluctuations by saying that all the derivatives in space of big F, the mean distribution, are going to vary on the system size L, right? While the fluctuations, at least across the field line, are going to vary with a typical size of the Larmor radius, which we found was the size of the eddies. The anisotropy is going to tell us that along the field line, the fluctuations will vary on the system size, however. And we saw earlier that this told us that the turbulent fluctuations were going to be low amplitude. And furthermore, that the mean profile is going to evolve slowly compared to the turbulence. So in other words, based on the estimates we had before, this equilibrium distribution should go like epsilon squared times the turbulence frequency, or epsilon, which will be our fundamental expansion parameter, goes like the ratio of the gyro radius to the system size. Okay, this was just coming from that diffusive estimate for transport that we came up with earlier. And all of this is going to be slow compared to the gyro motion given by the gyro frequency omega. So these are all the orderings we need. And when we do that, we just plug all this into the kinetic equation and we gyro average it, right? And what we find is the following system of equations. There's a lot of stuff on here. You're not going to have to remember what all of it is. I'll tell you what the physics of these things are real quick. So delta F, you can actually write it, it's useful to write it in this way. So this phi here, so this is the electrostatic potential, this is the charge, temperature, and this is some equilibrium Maxwellian distribution of velocities. This, you can see, is basically a Taylor expansion of a Boltzmann response. Okay? And this is going to be the non-Boltzmann part of the response of the plasma. So we can write down now an evolution equation for this non-Boltzmann response, again, just by taking the kinetic equation, doing all the orderings that I showed you earlier, and making sure you throw away parameters that are small in this expansion parameter epsilon. This is done, I believe, in Matt's notes. And here's a resulting equation you get, which tells you how h evolves in time. So just think of h as delta f from here on. It doesn't really matter that this thing exists. So you can see some terms which you might recognize. You have parallel streaming shown here. You have motion due to magnetic advection by magnetic drifts. That's what Vm is. Here's the gyro average. That's what's denoted by these angle brackets of the E cross B drift. So this is just the gyro average guiding center speed. Okay. This describes the effect of collisions, and this is telling us something about the energy source that we have in our system. So remember, what was driving these instabilities? It was gradients, in the case I showed you, in the temperature. Gradients in density, for instance, can also drive instabilities. And so that's all contained in this term, right? Because this is the gradient of that equilibrium distribution, which includes the density and the temperature. So this is the equation we want to solve. And to solve it, we have to also write down some expression for this electrostatic potential, right? That's going to be given by Poisson's equation, which I showed you on Wednesday, reduces to quasi-neutrality as long as the Debye length is short compared to any scales of interest in your problem. And so this is some integral equation which tells you that if you integrate up all the velocities of the particles, then you're going to get the electrostatic potential, pretty much. Right? And so now, if I ultimately want to figure out, so it's interesting to study the turbulence on its own because it's kind of a fun problem. But what we really need is the pressure profile. That's what we want, the equilibrium pressure profile. And to get that, we have some conservation of energy equation or force balance equation, which tells you how that equilibrium evolves in time under the influence of this flux of energy. So QR here is the radial flux of energy, which is coming from this turbulence, right? And you get that by taking basically your distribution function delta f, multiplying it by the energy of the particle, multiplying by its radial drift speed, which comes from turbulence, and then integrating over all velocities. Okay? So this J here, by the way, is just the Jacobian of some transform. Don't worry about it. And that's going to be sustained by some source, such as the fusing of particles I was telling you about before, which heats things, the exchange of energy between different species due to collisions, and, for instance, turbulent heating can also exist on this side of the equation. So we have a closed system of equations, which tells us how fluctuations evolve in time. These fluctuations depend on gradients in the equilibrium. The equilibrium itself depends on, the evolution of that equilibrium itself depends on the slow diffusion of particles out of the plasma due to the turbulence. So this is a coupled system of equations. You should note that everywhere here I'm talking about electrostatic potential. I'm not saying anything about electromagnetic fluctuations at the moment. You can derive gyrokinetics with electromagnetic fluctuations, and I'm guessing that's what Matt has done in his notes. But there are a couple of things I want to note about first gyrokinetics and also about magnetic confinement fusion gyrokinetics. So first of all, the gyrokinetic ordering, if you go through and look at it, the term in this which goes like 1 over c d vector potential d time doesn't exist in the gyrokinetic ordering. It's small. Okay, so the electric field is electrostatic. Now, in theory, you could still have electromagnetic fluctuations entering in this equation, and in fact, you do in general, right? But I'm going to look at the simplified case. If you take beta to be really small, okay, then what you find is that this means the fluctuations are approximately negligible. All right? So in other words, this is all we have. We don't have to worry about any of the other Maxwell's equations or anything. And so schematically, this is how we solve this on the computer. Okay? We have So I'm looking here at some mean quantity, such as the temperature on this axis. Here's the radius, which remember is going to be the distance from kind of the middle of the plasma volume out to some particular toroidal surface that we're interested in looking at. And this is time. So in theory, if I again did a direct simulation, I would need a fine mesh everywhere in radius and everywhere in time to resolve things like cyclotron frequency effects, turbulence, and everything, right? Forget the cyclotron frequency for a while. Let's imagine we just have to resolve the turbulence. Okay, we would still need to have a fine mesh to resolve turbulence in space and in time. Instead, what we're going to do, and what we've done successfully analytically by going to this mean field theory approach, is we've decoupled these two problems a little bit, right? In other words, what we're going to be doing is we're going to say that in these strips here that I'm showing you in blue, we'll have a fine mesh for the turbulence. And so we're going to solve the turbulence on a fine grid here. And we'll also have these little strips shown here in yellow, in which we're going to have a fine mesh in time to resolve the rapid turbulent fluctuations. And wherever you have intersections between these things, these little green regions will correspond to grid points in a coarse solver for the equilibrium, right? So as far as this equation here is concerned, it will get fluxes which are given to it, which are just averages over the fluctuations that are happening in each of these little regions. Okay, so I only simulate turbulence in these regions. These things then act as grid points in my transport solver. And so each of these little regions, I'll talk about in a bit more detail, are itself a 5-dimensional gyrokinetic simulation. And so here's kind of the domain on which we're going to solve the turbulence here. I'm going to talk about this in a bit more detail in a moment, so I'll just leave this here. But basically, it's a complicated shearing box simulation. And so what does that bought us? Well, the fact that we take into account the time scale separation and the spatial scale separation between the mean quantities, the equilibrium, and the turbulence or the fluctuations means we can throw away some more time scales and some more spatial scales in the problem. So this saves us another factor of 10 to the 6, and this brings us down to 10 to the 18 grid points, which is really something which is now doable on current supercomputers. Right. So I just want to talk a bit more about what's going on here. So this is called the so-called local or flux tube gyrokinetic simulation. You can not do this, right? You could do a global simulation. They exist in gyrokinetics. They're proponents of both this approach and the other one. This one I'm going to talk about because it's a bit simpler. I like it better anyway. And the basic idea here is that we want a periodic box. And the reason we're going to say it's periodic is because we're going to assume that, first of all, over the length of this box, the density and the temperature of the equilibrium are basically fixed. Okay, they're not moving. At the same time, I'm going to assume that you can have a gradient in the density and the temperature across the box. So in other words, locally, I'll say there's a density and a density gradient, or a temperature and a temperature gradient, but those things don't vary across the simulation domain. So as a result, it's just like a homogeneous box. And so as long as you include several turbulence decorrelation lengths inside your box, then it doesn't really matter what boundary conditions you take at the end, because whatever's happening on one end of the domain doesn't affect what's happening on the other end of the domain. So this is so-called statistical periodicity. That's the assumption that we make. And because we need to have the turbulence decorrelate between the ends of the domain, it means that we want to have a box which is many gyro radii wide in the directions perpendicular to the magnetic field. But along the magnetic field, it has to be quite elongated, right? Because the turbulence itself is elongated along the magnetic field line. So that's why you have this funny shape. This shape is just a flux tube which is following a magnetic field line as it wraps around the device. Okay? And if you wanted to, you could use statistical periodicity in this flux tube and just take this flux tube and reproduce it over and over and over again, and you can make an entire flux surface if you want from that. And so, for instance, this movie that I showed you earlier was actually a flux tube simulation. They just used periodicity to map out the rest of the flux surface. And so also, as I mentioned, this is a gyrokinetic simulation, which means that we have to resolve the distribution of particle velocities. And here I'm just giving you a snapshot of what that distribution might look like. So remember, we've eliminated the gyro angle as one of our phase space variables. So we only have a 2D velocity space to worry about. And so here I'm showing you the parallel speed of the particles, the perpendicular speed of the particles, and you can see that you get this sort of fine scale structure which can develop in the velocity space due to these phase mixing mechanisms that I mentioned earlier. And so I mentioned it's a shearing box. Why did I say it was a shearing box? Well, there are two ways in which this box can be sheared. One of them is magnetically, and the other one is via flow shear. And so here's a picture of how that works. So if I had a straight magnetic field line, then this would be a simple task, right? I would just take my box, follow the magnetic field. It's just some kind of rectangular domain. And if I put an eddy, for instance, in that domain, and it moved along the field line, then assuming the turbulence doesn't do something to it, it would just kind of stay oriented the same way, right? Everything's fine. Now, if I imagine that at this location, the magnetic field is, say, pointed more vertically upwards, and down here it's pointed more vertically downwards, right? This is saying that the pitch of the magnetic field lines are changing as I move radially across the plasma. This is called magnetic shear. Then as I do that, just as you would maybe with flow shear, which you may be more familiar with, it's going to mean that this side of the domain goes up, this side comes down, and this gets exaggerated as I move further and further along the field line. Okay? So the result of this is that I take an eddy, which is aligned, say, mostly horizontal here, and I tilt it so it starts to become looking a bit more vertical. And what that does is it takes the wave number of my mode, which originally is something very small, and it makes it bigger as a function of location along the field line. Okay? And so what you can do to implement this in a code, for instance, if you are using just a code which is spectral with k in k-space, then you can simply make kx a function of distance along the field line. It's comparable to what I know that you do also in space and astrophysical plasmas. If you have a flow shear in the system, we also have flow shears in the system, so we have to do a similar thing. It's the exact same idea, except now this direction is showing an eddy, which is shearing as a flow shears it in time, right? So here you could imagine you have a flow going up on this side of the box and a flow going down on this side of the box. And so in order to take this into account, your wave number kx has to now increase in time. So I pointed out this picture earlier, and I've mentioned this gyro averaging multiple times. That's another thing that gyrokinetics complicates for us, because we fundamentally now have a non-local kind of situation. Because you're not just looking at turbulence at some point, you're looking at the turbulence averaged over this gyration. And this is kind of a pain in real space, right? Because to resolve this, you need to make sure that you have grid points at various points along this path. And you can also imagine now that if you go to the situation where this gyro radius is fairly large compared to the size of your eddies, or in other words, if you go to k rho large, then you need many, many points along this gyro motion to actually resolve the variations in the turbulence along it, right? And so it's very difficult for these codes to work in real space and to resolve large values of k rho, all right? And so the way to get around this, or a way to get around this, is again to do things in Fourier space, so to go to this sort of periodic box type approach. And it turns out that in Fourier space, if you take your potential, and this potential, of course, is a function of the real position of the particle, right? And I'm going to gyro average that at the center of the particle's location, right? So here's the position of the particle. The gyro average is going to be evaluated for particles who are centered on a particular magnetic field line, given here by its guiding center location. And so if I take phi, I expand it in Fourier harmonics, then we see this is sum over k of the Fourier coefficient, which, for instance, may depend along position along the field line. So I'm only going to transform in the perpendicular domain, times e to the I k perp dot r. So this gyro average is 1 over 2 pi times the integration over the gyro angle. And r, I can write in terms of its guiding center position in this way. So r is just guiding center position plus the vector out, the gyro radius vector. And the the trick here is that this gyro radius vector depends on gyro angle, whereas guiding center position, we're doing this whole average at fixed guiding center position, right? So this term can come outside our integral. This one is the only thing that has any gyro angle dependence, and we can do this integral analytically. Okay, it turns out that the integral over theta of EVI k dot rho of theta is just a Bessel function. Okay, so this J naught is a Bessel function. This is the argument of that Bessel function. And so applying the gyro average only means that you have to multiply by some known function. Okay, so in K-space, this operation is much, much simpler than it is in real space. Yep?
So in a real plasma, the particles could be having a wide range of plasma radii depending on the energy. And there would also be crossway drifts. So particles would be going away from the surface.
Yep.
So when you have a flex tube simulation, so the plasma radii may not fit within the box, or the particles may go outside of the box.
So there's two things that happen. The first question, you're saying what happens if you have a Larmor radius which is bigger than the size of your domain? Well, in that case, the idea is that if the turbulence has a spatial scale which is much smaller than that Larmor rate, so we want to make sure the spatial domain is big enough to include several eddies in it, basically, so that the turbulence decorrelates. If you do that, and you take a Larmor radius which is much bigger than that, then what you're going to find is that basically, as I pointed out earlier when I was looking at that instability picture, if you average over the turbulence, you basically eliminate the effect of the turbulence when you do that. So in other words, that piece of the distribution function will end up being negligibly small because it's averaging over all this different turbulent motion. And so that's why we don't care about particles whose gyro radii are much, much bigger than the scale of the turbulence. As for drifting out of the domain, absolutely right, particles will leave the domain, but because it's a periodic box, they just come back in the other side. But so not in these simulations. Because they're local, we're making the approximation the magnetic field is constant across the simulation domain because we're not changing very much macroscopically in the plasma when we do this. Okay? And you may be worried also that, imagine, we're talking about wanting to calculate transport, right? So if we're taking particles which are leaving one side of the domain and putting them back in the other, you might say, oh, well, where's the transport? Well, all we're looking at is the rate at which things are leaving. So we'll still be getting the radial transport from that, for instance. Does that answer the question? Okay. Any other questions so far? Okay. So obviously there are many, many more details which go into actually writing one of these codes, but these are the fundamental ideas. Okay. We have a periodic box, we complicate it in a few different ways, and we have to resolve a velocity space in some way, right? Otherwise, it's not that dissimilar from the periodic boxes you might put, for instance, in an accretion flow in an astrophysical system. So what I'm going to talk about now are a couple of different things. First, I'm going to give you an idea of a particular problem that we're looking at in magnetic confinement fusion, which deals with these turbulent concepts I've just talked about, right? And then I'll go on to talk a bit more about the fundamental properties of the turbulence and maybe how it relates more to space and astrophysical systems. So I'd showed you this picture, this movie last time, and what you can now maybe recognize is that this initial phase of the plasma here, this is the turbulence. It's moving things around, it's a bit noisy, and you'll see in just a minute that this turbulence mostly goes away. The plasma gets brighter and it just kind of sits there. So right now you have a lot of turbulence, and there you go. So there it becomes much cleaner. What's happening right there is that the turbulence is being suppressed somehow. Okay, so we have the turbulence I've just been talking about, and then all of a sudden this turbulence fluctuation levels drop dramatically, and we get much steeper temperature gradients, at least at the edge of the plasma. Okay, and so what's happening there? Well, frankly, there's a lot of speculation still about what's happening there. This problem, what's called transition from a low confinement mode, or an L mode, to a high confinement mode, or an H mode, was a surprise when it was seen experimentally, and theorists such as myself think we kind of sort of understand what's going on, and I'll tell you kind of sort of what we think is going on, but really we don't, after decades, have a good explanation for it. So this is a huge, huge open problem in the field. It's been around for a long time. seems to have something to do with the turbulence, but we don't fully understand it. But one possible explanation for it is the one I was touching on earlier, and it's the idea that if you take a plasma and you have eddies which are connecting radially the inside of the plasma to bits in the outside of the plasma, and then we apply sheared flow across that system, then what's going to happen, right? Well, I don't have a picture of this, unfortunately, but basic idea, I have an eddy. Can you guys see that in the back? Yeah, okay, good. You apply flow shear across that eddy, and what's going to happen? The outside goes up, the inside goes down. Okay, and there are other eddies on either side of this. And the idea is that if I started out with a gyro radius, which is sampling that turbulence, it's comparable to the size of that eddy, and I shear it, and I keep shearing it long enough, then what you're going to find is that that gyro radius averages over multiple different eddies, because you're basically shearing and stretching that turbulence. And so once I start averaging over more and more eddies, then I'm going to reduce the effect of that turbulence. And once I average out that turbulence, I don't have any transport anymore. Okay? So the idea is that by applying a flow shear across the plasma, we might basically shear, possibly break the eddies, but even if we don't break them, we can still average over them with our gyro radius. Okay? And so that might suppress the turbulence, and there's evidence for this in magnetic confinement fusion devices. So here I'm showing you data from an experiment in Japan. What we're looking at here is the ion temperature, taken again from the middle of the plasma volume out towards the edge. And you can see that there are regions of this temperature which are fairly shallow, and then you have one region of the plasma, shown here in gray. It's called an internal transport barrier, where the temperature gradient is very large, right? And there's a lot of complicated looking stuff going on over here. Basically what you're looking at here, this is the shear in the radial electric field, which is a proxy for a shear in the flow of the plasma, okay? So you can see that you have this huge spike in the flow shear in the plasma in this region, and associated with that, here on this dotted thing here, you're seeing basically the diffusion coefficient versus radius. And so it's something which is increasing, 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 and this region takes a little dip before going back up again. So there's some experimental evidence, certainly, that there's some correlation between flow shear in the plasma and reduced turbulence. The question is it causal or not? And so that's something that we don't really know, right? So this is one of the big topics people look at in turbulent transport. There are many others that I don't have time to touch on right now. And so I'll end the fusion part of the talk just by kind of pointing out where we are. So this is a slide I think I stole maybe from Greg Hammett here at Princeton. This is showing the performance measured by so-called triple product. This is the density times the temperature times the confinement time in the plasmas. This is the widely used measure for the performance of your fusion plasma, and this is versus year. And so the blue line here is showing fusion, right? Red line is showing the speed up due to chips on computers, and these are energies that you're achieving in, for instance, LHC, Tevatron, and so forth. And so it's a wide joke, certainly known to fusion physicists, that fusion is the energy of the future and always will be, right? Or it's 20 years away and always will be, or whatever it is. And of course, there's some truth to that, because it always does seem to be 30 years away. And if you ask me today, I'd probably say it's 30 years away, right? But at the same time, I mean, the progress we've made is phenomenal. And we have another experiment coming online, which is set to kind of continue this trend, except for the fact that it's been delayed and delayed and delayed, so it might actually make things fall off here. This is called ITER. It's an exciting experiment in our community, but these things are really big projects. So ITER has been in the works for 20 years now, and that's really why things are so far away always, right, these days, because it takes so long to build the next thing. It's just too complicated at the moment. So I guess that sounds like a bit of a depressing conclusion to make. My statement would be that, and this is of course a self-serving statement, that we're building one ITER right now, and we're taking a long time partially because it's so important to the community, right? There's only one of these things being built. It's a collaboration between a bunch of different international partners and so forth. if, of course, we had infinite amounts of money, then we could build 10 of these at once. And then we wouldn't, first of all, be so slow on each given one, and we could try 10 different things at a time. So fusion is a long way away, but I think that it is possible to speed it up.
On that scale, where is a commercially viable reactor?
Excellent question. So JET here is roughly fusion break-even. Okay, so it didn't quite achieve it, but it got maybe 90-something% of the energy out that put in. ITER is going to be a factor of 10 greater than that, so it'll be somewhere a factor of 10 up here. And then that's not far off a commercially viable fusion reactor in terms of the ratios of efficiency. The difficulty, of course, is that the cost of ITER is huge, and we can't have a fusion reactor that's commercially viable costing that much. So I don't think we're, a decade or so off up here. But the real issue now is bringing down the cost. First, we have to demonstrate we can do it, but then we have to bring down the cost. So there are a lot of challenges ahead for fusion, many of them which I haven't touched on at all because we're talking about physics here and not engineering mostly. And so there are a lot of technological constraints and a lot of things which can actually make things better. So some of the bad things we have to deal with, if you took one of these plasmas and took all the energy and just shoved it out to one of these instabilities, as I mentioned, then you just melt the wall, right? You also have neutrons which are being shot out of this plasma. These neutrons bombard the wall, and depending on the type of material, you can degrade the integrity of the material, right? So there's a lot of effort going in right now to technological advances in terms of what the walls are made of, for instance, how to take the heat loads out of these plasmas in a safe way. Also, as we said, the fundamental thing you want to improve here is how long it takes the heat to leave the plasma, right? If you put stronger and stronger magnetic fields in, then you make these Larmor radii smaller and smaller, you make the turbulent eddies smaller and smaller, and so you can find the plasma better. So if we could increase the magnetic field strength by a significant amount, again, it would be a huge game changer in the field. So there's a lot of effort going into creating higher magnetic field magnets, for instance, using superconducting. We still need to work on controlling these macroscopic instabilities because even one catastrophic one could destroy the machine. We're looking at innovative ways to, for instance, use flow shear and other types of things to reduce turbulence in our system. Because if you could have these little internal transport barriers all over the device, then you wouldn't need these huge machines which cost so much. And we want steady state operation, which I've largely not touched on today, which might involve going to something like the stellarator that I mentioned on Wednesday. Right? And so those things are in progress going forward. So there's a big stellarator experiment being built in Germany right now called Wendelstein 7X, which is roughly of the same scale and ambition as this jet tokamak, which currently has the best performance of any of the tokamaks, except it's a stellarator, so it's even more complicated and has a lot more interesting things which might happen. And then ITER, as I already mentioned, which is being built in France right now, and hopefully will come online at the end of this decade, basically. So that's it for fusion-specific stuff. And what I want to do now is just take a moment to show that there's some connection between what I've been talking about with fusion and what most of you are interested in, which is space and astrophysical systems. Okay. So one of the problems you guys are interested in, or at least some subset of you are interested in, is turbulent heating. Okay. And so all I've been talking about with gyrokinetics, you can actually apply to this problem of turbulent heating. And to do that, you can look at, say, a turbulent plasma, which is dominated, say, by electrons and one species of ions, which are hydrogenic. And you can ask the question, how much are the passive minority ions heated by the turbulence? This is a question which is interesting in the solar wind, for instance, where we see that the temperature of the plasma basically scales with the mass of the temperature of the minority ion scales with its mass, right? And so in gyrokinetics, we're restricted a bit because we can only look at isotropic heating. The reason we can only look at isotropic heating is, as Matt discussed, the magnetic moment in gyrokinetics is conserved. We assume that nothing perturbs the motion of the particles significantly over one gyro orbit, and so you can't break the magnetic moment. There's still a turbulent heating mechanism which exists, and that's Joule heating, right? And this Joule heating mechanism is just delta J, where this is the fluctuation in the current parallel to the field, times delta E parallel, right? So you can look at the size of this heating, and in particular, the current goes like the charge times the speed times some size of the fluctuation. This thing is going to be determined in this case because it's a passive problem just by the background turbulence. And so this V thermal has a square root of mass in it. And so already you can see, without doing anything else, you would expect some kind of heating in your plasma, which preferentially heats heavy ions, right? This isn't quite what we need because it's supposed to be mass proportional. But we have this other factor here, which is the amplitude of the fluctuations of our minority ion. And we can see that what's happening, we have, say, a distribution for heavy ions. This is the distribution as a function of parallel speed. And because heavy ions are so much heavier, if they have the same temperature to start out with, then that means that they're going to have a much smaller thermal speed, and therefore they're going to have a much narrower distribution in parallel speeds, right? Conversely, light ions will have a much broader spectrum here. So if we accelerate these particles simply by putting them in an electric field, then the mass drops out, right? Because if this is an ionized, fully ionized ion, then the charge to mass ratio is half. Okay? So the kick in V parallel that you get from this acceleration is the same for both the light ions and the heavy ions. So delta V parallel is the same. But as you can see, this leads to a much, much bigger fluctuation for the heavy ions than for the electrons. In particular, the fluctuation goes like the displacement in V parallel over the thermal speed. And again, using the mass that appears in the thermal speed, this goes like mass to the half. So giving you total scaling for the heating, which goes like the mass. So this is consistent with what's seen in the solar wind. I've done almost no detailed physics. We've just looked at some simple problem. So this is showing some old data from the solar wind. What we're looking at here is the temperature normalized to mass for a couple of different ions. This is oxygen 6+ and helium 2+. And so we have temperature proportional to mass. And so we can run gyrokinetic simulations now, which include all the physics I've just discussed, and find that the heating is indeed proportional to, it turns out, charge squared over A, which you can predict analytically. And so again, if charge and this is mass number, if charge over mass number is half, in other words, if it's fully ionized, this is just saying heating goes proportional to mass. Okay? So this is one possible explanation for what's going on in the solar wind. There are many other explanations, reconnection, stochastic heating, and so forth. And so I'm not saying this is what's happening, but you can certainly get some of the physics you want for space and astrophysical plasmas simply from gyrokinetics, the same sort of things I've been talking about. And for that matter, we can look a bit at fundamental properties of this turbulence, which again will be present not only in fusion plasmas, but in certain astrophysical systems. So what I'm going to do is I'm going to take our gyrokinetics, I'll make a few simple conjectures, and then I'll tell something about the turbulence. This is going to be similar to a Kolmogorov-like arguments, except now we're going to be looking at kinetic turbulence. And so neutral fluid turbulence, if you want to get some kind of scalings, you assume that the turbulence is isotropic. So I'm going to assume it's isotropic, but only in the plane perpendicular to the magnetic field, because we know the magnetic field is going to introduce some anisotropy into the system. We're going to assume that the position and velocity space scales are linked via this nonlinear phase mixing mechanism that I discussed earlier. We're also going to assume something which is something we got from the astrophysical community called critical balance, which was developed for MHD turbulence. And this was saying that the parallel streaming time and the nonlinear turnover time are going to be comparable at all scales, right? I think I talked about this later, so I'll leave it for now. And furthermore, we're going to assume that the parallel length scale is set by the system size, which in a tokamak is the connection length, but I don't think I'll go into that. So what can we get from these assumptions? Well, there's actually one more I'm going to make, which is that the velocity space is smooth and isotropic. So everywhere in our equations where we have a derivative with respect to velocities, it's just going to go like h over the thermal speed. From quasi-neutrality, because the velocity space is smooth, I can approximate an integral over h as just thermal speed cubed times h. And so from this, I get that h normalized by Maxwellian is phi. So in other words, basically plasma fluctuations are the same size as the electrostatic potential fluctuations. This critical balance idea is saying that imagine that you have an eddy, and you have some particles which are moving along in that eddy, right? So that eddy is turning over in the perpendicular domain, and the idea is that if it turns over once, it's going to decorrelate, right? Well, in the time that it turns over once and decorrelates, that particle is streaming also along the field line inside that eddy, and so the fact that it decorrelates once the eddy turns over is going to limit how far along the field line the turbulence can be correlated, right? So in other words, the correlation lengths along and across the field line are related. And that's all that critical balance is saying. And so we can define a nonlinear time scale to be h at some scale over the nonlinear time of that scale goes like VE dot grad. This is basically the nonlinearity in the gyrokinetic equation. And so critical balance is just saying that whatever parallel dynamics you have are balancing this rate at which the eddies are turning over, right? So in fusion, this turns out to be a sound wave which is propagating along the field line, and that's the characteristic time that you have. Of course, in other plasmas, this might be an Alfvén speed or so forth. And so if we assume that you have some energy being injected at large scales in the system, that you have a cascade of energy to smaller and smaller scales, which is eventually dissipated by collisions, then as long as these scales are separated, you can imagine there's some kind of inertial range in your system. In that system, whatever energy comes through one scale has to leave that scale, right? And for things to be in a steady state, the energy flowing through this has to be independent of the scale you're at. So it turns out for the Kolmogorov type argument in neutral fluid turbulence, what you do is you assume that you have, well, you show that you have some conserved quantity, which is the energy of the flow, and then you assume that that energy is scale independent in the inertial range. Here, it turns out that you have another conserved quantity. It's the so-called free energy. Basically, it's the perturbed entropy of the fluctuations, which I don't have time to show, but this is the free energy. Was there a question? Yeah. If you assume this thing is scale independent, then again, I'm not going to go through all the algebra. I'm just going to give you a flavor for things. You say that this free energy rate is a constant. And so from this, you can get some kind of estimate for the size of the fluctuations as a function of scale in the system. And if you wanted to, you could also do some kind of theory for what happens here at the outer scale. I'm going to omit that today. You could match sort of the power law exponents you get in the inertial range to here, but I'm going to skip that. So whenever you do this, what you find is that the amplitude of your electrostatic potential as a function of scale, forget all this stuff, this is fusion specific. This is not. This goes like k perp rho I to the minus 2/3. Okay, so we have some power law scaling we can estimate for the distribution of the energy of the fluctuations in among spatial scales. And all of this right now is for k rho much less than 1. And I can convert this into an energy spectrum just using dimensional analysis. And so I get some expression for the energy spectrum. And I can use critical balance now to get an energy spectrum in k parallel as well. Or in other words, I can relate how k parallel and k perp should be related. And I can test these things. So what we've done is we've run simulations. We've predicted these slopes. We've run simulations and measured those slopes. And you find that indeed this is just a bunch of different simulations where we've changed different parameters. These things are things like the temperature gradient, the pitch angle of the magnetic field, and so forth. And you find indeed that the simulations follow this simple kind of scaling law estimate. You can check the critical balance assumption as well, which is what's happening here. We're looking at the correlation function as a function of, say, perpendicular wave number and distance along the field line. And the theoretical prediction from critical balance is shown by this black line. You can see that it maps out very well the contours of the simulation. This is just another test of critical balance. This is the predicted slope from critical balance, and here's what we find numerically. And I don't have time to go through the details, but again, you can repeat this analysis that we just did here for eddies which were large compared to the Larmor radius. You can do that now for eddies which are small compared to the Larmor radius. And that was done by Alex Shekharchian back in 2009, again looking at, coming at things from the astrophysical context. but everything he does is still valid for the diffusion context. And so what you find is you get somewhat different slope, a bit steeper, which goes like k to the minus 10/3. And so from this, you can actually, if you know a bit about how your instabilities are driven, like we do in the fusion world, then you can also figure out sort of an effective Reynolds number for your system. You can look at a difference between this dissipation scale or cutoff scale and the outer scale in your system. Okay? So we can write down kind of a cartoon picture of all the properties of the turbulence that you kind of care about in the Kolmogorov sense for a plasma in the same way you can for neutral fluid. And in fact, it's even more complicated than this because all I've talked about is real space, but because it's a kinetic cascade, you can do scaling laws also for how things are distributed in sort of the dual or the Fourier spectrum of the velocity space. So there are tons of interesting things to do. It's not specific to fusion. It can be astro or space or whatever you want. So I got questions last time about how space and astro how astro and fusion kind of overlapped and how they influence each other. And so here's at least one way in which the communities are working together right now to try to solve this sort of fundamental problem. So with that, I'll conclude. Thanks.